So what is a binary search tree? Today I'm going to be showing you slides from the other textbook. Okay, so far we've been looking at only one textbook, and the second one is by Wayne and Sedgwick. Okay, so I'm going to be showing you slides and a demo using those resources. So let's look at the definition, a little bit of slides, and then we'll get back to our Jamboard. Okay, is this screen appearing to you? Can you see the screen?
Yes, doctor, we can see it.
Okay, good.
Yes.
So like I said, this is coming from this book. It's called Algorithms. This is the 4th edition for it. All right. So here's a definition for binary search tree. A BST is a binary tree in symmetric order. Symmetric order. Now, what is symmetric order? If you look at the tree on the right side, okay, is this a binary tree? Yes or no?
Yes, doctor, yes, it is.
Is it a binary tree or not?
Yes, a binary tree,
yes.
Remember the condition for binary tree. A node may have up to 2 children. So if you look at it carefully, yes, this is a binary tree. Like, condition for binary tree is either it's empty or there's 2 disjoint binary trees. Yani something on the left side, something on the right side. Something on the left side must be a subtree. Something on the right side must also be a subtree. So this is what we already know. What is symmetric order? This is something new. Symmetric order means that each node has a key, and every node's key has this condition. This key is larger than all the keys on the left side, and it's smaller than all the keys on its right side. Type example. Look, the root of the tree is S. See the picture on the right side. The root of the tree is S. Everything on the left of S must be smaller than S. Everything on the right of S must be larger than S. The same rule applies at every single node in the tree. Example, look at the node that contains E. Everything on the left of E must be smaller than E. Everything on the right of E is larger than E. Now the question is, if we have characters, how do we say that this is larger, this is smaller? So what we do is we look at the ASCII code for this character. Usually A comes before B. So I will say A is smaller than B. C comes after B. So I'll say C is bigger than B. So using this logic, okay, if I'm looking at the node that contains E, on the left of E is A and C. Both of them are smaller than E. But if you look at the node A dot right, okay, is C. C is larger than A. C is larger than A. A is smaller than C. So keep this in mind. For binary search tree, okay, in addition to all the properties that we studied for trees and binary trees, we have one more property, which is it has symmetric order, which means that for a node to be in a binary search tree, everything on its left side must be smaller than it, and everything on the right side must be larger than it. So far, so good?
Yeah.
If it is okay.
Yes,
Yeah.
doctor, can I have a question, please?
Yeah, yeah.
Now, you said in C, the key is larger than A. Isn't C to the left of A?
No, C is to the right of A because C is bigger than A. But if you say C and A, both of them are to the left of E, which means A and C, both of them are smaller than E. Same goes with R and H. If you look at it carefully, R is bigger than A. That's why R is appearing on the right side. But H is smaller than R. So H is on the left of R. At the same time, H is larger than E. Therefore, H is on the right side of E.
Okay. So H is larger than E but smaller than R.
True. Yes. Same goes with C. C is smaller than A, but it's larger than, sorry, C is smaller than E, but larger than A.
Okay, clear. Thank you.
Okay, let's look at an example. I'm going to show you a small animation. Let's have a look at it. So have a look at this tree. Is this a tree?
Yes, doctor.
Yes, doctor.
Is this a binary tree?
Yes, doctor.
Okay, third question. Is this a binary search tree? Now you have to check.
We need to check the keys if they meet the requirement.
Exactly, you have to check. But let's assume that this is a binary search tree. Okay, I'm not going to go in details. We're going to look at it a bit later. So let's assume this is a binary search tree. Let's say I'm searching for H. I'm searching for H. Now what I do, we always start at the root. So I'm going to go from here. Okay, what I'm going to do is I'm going to compare H with S. H appears before S, yeah, and it's smaller than S. Now what I know is that H cannot exist on the right of S, right? Because according to my symmetric definition, everything on the right of S must be larger than S. Everything on the left of S must be smaller than S. This means I don't need to go and search on the right side. I need to search on the left side. So what I'll do is I'll go left. Now you repeat the same process. We're going to compare H with E. It happens that H is bigger than E, which means again, I don't need to go on the left of E because everything on left of E is smaller than H. I cannot possibly find H on the left side. It must be on the right side. So we go right. Again, we're going to compare. Okay, compare H with R. So again, H is smaller than R. So again, this means we have to go left, which means H cannot be on the right side of R. So we go left. Okay, then we compare H with H and we found it. So far, so good?
Yes, doctor.
Yes, doctor.
Now this is going to work really fast. This is working really, really fast. Unlike the linked list. In the linked list, the runtime was always big O of
Big O of N.
Big O of N. Good. So I'm going to show you why this is faster. Okay. Let's first look at the scenario where what we're looking for is not there. Okay. Let's say this is the tree. I'm searching for G. I'm just looking at it. You know, G is not there. But of course, computer is not as smart as you are. So it's going to go and look at it. So start from the root. We compare G with S. Type G is smaller than S, so we go left. G is larger than E, we go right. G is smaller than R, we go left. Okay. G is smaller or bigger than H?
Larger than H.
Oh, come on. You have to put G.
It's smaller.
G is smaller than H, so we go left. Okay, but left is null, it's empty. Mine, it's not there. So we can return, my search method can simply return null or not found. Okay, so far so good? Okay, let's get back to Jamboard. And I'm going to show you how come binary search tree is faster than the linked list. So remember, now I'm going to create a binary search tree. Let's put some dummy values here. So the symmetry value or property should always be held. So I have 4. Maybe I have 10 over here. I have 2 over here. Okay, so far just keep checking. Is this a binary search tree or not?
Yes, it's a binary tree, Doctor.
Okay, there you go. So this is a binary search tree. Binary search tree. So imagine I will store all these values in a linked list. Okay, so my list is going to contain these values: 7, 4, 2, 1, 3, 6, 5, 10, 8, 9, 12, 11, 13. Okay, there's no particular order to it, but I've just put it in this way. So if I'm searching for, let's say, 13, okay, how many searches do I have to do? So starting from here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I have to compare 13 times before I find the value. In a binary search tree, if my tree looks like this, look how many searches would it take? So start from here, 13, we go right or left?
Right.
We go right because 13 is bigger than 7. Okay, 10 and 13.
Right.
Right. 12 and 13.
Right.
Right. And we found it. How many searches did it take? 1,
4.
2, 3, 4. Okay, 4 searches. I've searched something else. Let's search 3. So here, 1, 2, 3, 4, 5. Okay, but if I'm searching 3, again start from the root. 3 is smaller than 7, so we go left. Smaller than 4, we go left. Larger than 2, go right, and we found it. How many searches?
4.
4. Okay, so far the worst thing is 4 searches. Type search 10. How many searches?
2, Doctor.
1, then we go here, 2, and we found it. Okay, so this means that the maximum number of searches is 4 in a binary search tree. Okay, in a linked list, it could be 13. Last value is 13, so it could be 13. All right, so this is, imagine the size of this list is 16, let's say, or 15, let's go with 15. Size of this list is 15. Imagine there was 2 other values over here. So the worst case scenario is it's going to take exactly O of n time. Like here in binary search tree, if you're searching for something, we know this thing, if the tree looks like this, the maximum number of searches is 4. Okay, 4 is something like this. 2 to the power of 4 is 16, right? Can I describe this as log of n?
Yes.
So if n is 15 or 16, its log would be 4, which means now the runtime is log of n. So that's the beauty of binary search tree. If you have a tree like this, its runtime is going to be log of n. I mean, is this faster? Imagine the size of your list was 1024. Log of 1024 is 10. Okay, so is that a big difference? If I'm searching for something in a list with the size of 1024, it's going to take me 1024 searches. But in a binary search tree, if the tree looks like this, okay, it's going to take only 10 searches. Like, how about 1 million? Okay, log base 2 of 1 million is 20. Here it's going to be 1 million elements. The 1 billion, okay, same. 1 billion would be 30. So there's a huge difference here. We're talking about 1 billion searches here and only 30 searches over here. So naturally, this is going to be much, much, much faster compared to a linked list. So That's the ideal situation. If you get a binary search tree, okay, that kind of looks like this, kind of a complete tree, is guaranteed to give you O of log of n time, which is much, much faster compared to the linear time, or big O of n. All right, now we're going to study, okay, how insertion works. How do you actually go and insert something in a tree? If you have a tree like this, how do we insert that? Let's get back to the slides.
But Doctor, before that,
Yeah.
the slide said you want a larger key, you go left in the subject. Why we go right here in this exam?
No, larger means go right. Larger, go right. Smaller, go left. So you check your tree. Anywhere, 8 is smaller than 10.
Yes.
Okay? It's on the left side. 9 is larger than 8, but it's smaller than 10. And it's larger than 7. Look at 5. 5 is smaller than 6, so it's on the left side. But 5 is larger than 4, so it's on the right side. 5 is smaller than 7, so it's on the left of 7. Clear? Any questions about this?
Yes. Okay, but you can see the slides. I think it said you go left if it's larger.
Where? This slide?
No, before the dimension. Yes,
No,
larger than.
it says all the keys, okay, on the left side. So your node, your parent node, is larger than everything on the left side.
Oh,
Okay, it's the same thing. You're just looking at it from the other side.
okay.
So what it's saying is everything on the left is smaller than E. Everything on the right is larger than E. But if you look at it from this perspective, okay, each node has a key. This node has a key. And every node's key is, this node's key is larger than everything on the left side. This key is smaller than everything on the right side. It's the same thing. Okay, let's see how do we actually go and insert something in a binary search tree. So imagine this tree is given to you, and we would like to insert G in there. If you remember, when we used to insert something in the linked list, the fastest way to insert was where? Yes?
And the head, Doctor.
At the head, yeah. If you insert this thing in the beginning, that's the fastest. It's going to give you constant time. But now with binary search tree, we cannot do that. Okay, why? Because we have to maintain the symmetry property. So we have to follow the same rule. Let's see how this is going to work. We're going to insert G. Of course, we're starting at the root. The root is S. So we'll repeat what we did for searching. We're going to compare G with S. So G is smaller than S. Yeah?
Doesn't the requirements for a binary tree prevent us from inserting one element at a time? That we should we'll have to insert two elements.
No, it's okay. We can insert one element. In fact, we insert only one element, not more than one at a time. So let's look at it. So we have G, we'd like to insert G. Again, we started the root. G is less than S, so we go left. E is bigger than E, so we go right. D is smaller than R, so we go left. D is smaller than H, so we check on the left side. Left side is empty, so we can go and create and attach this node over here. Okay? Now, how does that work? I'm going to say h.left equals G node, G.parent equals H node. All right, we're gonna talk about the code a bit later. Okay. So far, so good. Any questions? So here I'm going to show you. If somebody wants to insert 15, where does it go? So we're going to start from here.
It will go to the right, Doctor.
15 is larger than 7, go right. 15
Then go to
is
the
larger
right.
than 10, go right.
Then
15 is larger than 12, go right. 15 is larger than 13, go right. There's no more right.
yes.
So we go and insert a new node and put 15 over here.
Yeah. Now, is this okay, Doctor, to leave it like this?
Yeah.
Or do I need to have to add another node or even an empty node by the other side to the left of 13?
No, you don't. Okay, this is important. What you're saying is very interesting. We don't have to balance the tree. What you're saying is balance the heights. No, we don't have to do that. Okay, so that is a positive point and a negative point. Now I'm going to show you something which is really good with binary search tree. If you get a tree like this, it's going to give you log of n time. But is this guaranteed that every time you're going to get a log in time? No. Okay, let me show you. I'm just going to reorder this data. Okay, it's just numbers from 1 to 15. I'm just going to reorder it, and let's see if you can insert it. So let's try to insert this data. 1, 3, 2. Okay, let's try to build a tree with this. So I'm going to start in the beginning, of course. The tree is empty, so we start with 1. Next is 3. Where should I insert it?
To the right, Doctor.
The right of 1, so 3 comes here. Next is 2. So 2 is bigger than 1, so we go right. 2 is smaller than 3, so we go left. Next is 4. So it started 1. 4 is bigger than 1, go right. 4 bigger than 3, go right. So we put 4 over here. 5 goes right. 5 is bigger than 3, go right. 5 is bigger than 4, go right. Okay, next 6. So again, 1, 6, bigger. 3 and 6, 6 is bigger, go right. 4 and 6, 6 is bigger, go right. Bigger than 5, so 6 goes over here. Okay, next is 8. So again, we start from the top. Right, 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 and we insert 8 over here. Next is 7. So again, start from here. Right, 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 but left, because 7 is smaller than 8. Okay, next is 9. So again, we start from the top. Because 9 is bigger, so right, 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 and 9 comes here. Okay, and then 10. So we can go all the way and insert 10 over here. Right. Is this a binary search tree? Remember the properties. It has to be a binary tree, and it must have the symmetry property. So we ensured whenever we were trying to insert something in there, we made sure the property holds. Everything on the left side is smaller, everything on the right side is larger than the node itself. So we know that this is a binary search tree. But now if you try to search some information in there, is it going to give you, again, log of n or not? Okay, so let's try to search 10. How many searches would it take to search 10? Check from here. So 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, the total size of my tree, or let's say my list, was 10 elements. And I'm getting 8. That's not good enough. Okay.
Yeah, it's much more than log of n.
So yeah, it's much bigger than log of n. In fact, it's close to n. What if I get rid of these? Okay, just remove these. Does it kind of look like a linked list now?
Yes.
Yeah, imagine this was a head. So we start from here, go right, 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 right. It looks like a linked list, which means now the runtime is going to be big O of n. So that's the problem with binary search tree. The performance of the binary search tree depends on the shape of the tree. If the tree is going to look like this, okay, that's going to give you log of n. If the tree is going to look like this, skewed, that's going to give you O of n. So our goal is to make sure the tree stays like this, but then it's not in your hand. According to the definitions, okay, we may end up getting a tree like this. Remember one thing, if the data is sorted and you're trying to insert this in the tree, you're going to get this tree. This is called skewed BST. Skewed means it's going in one direction. Okay, see for yourself. Let's try to insert this data. 8, 7, 6, 5, 4, 3, 2, 1. Okay, can you build a tree for this? Let's start from 8. 7 goes left. 6, 5 goes left, 4, 3, and so on. Okay, so what kind of tree is this?
Skewed.
I just told you on the last slide. Come on.
Yeah, skewed.
Skewed. Skewed BST. And it's going to give you big O of n time, which is not good enough. So to answer this, next week, inshallah, we're going to talk about the AVL trees and how do they work. Okay? But for now, let's just focus on this. How do we implement that? Okay.
Doctor,
Yeah.
would there be a way when inserting a node in the tree, that there is no need to go through all the tree from the root? For example, if we have the biggest number or key in the node is 8, and I want to insert 10. So I know where is the 8, and I just go directly to that place without going through the whole tree.
But the problem is, key like 8, how many of them you're going to remember? Are you going to remember all of them? Then it's going to become difficult.
This
So
will be difficult, especially with big trees.
yeah, it's going to become difficult. So we have to come up with something else. Yeah, it's an idea, but again, the thing is, if you're able to know the position of every element, then why not use arrays? Array would be the fastest thing if you know the position. But if you don't know the position, now what should we do? Array doesn't work. It gives you O of n time. Linked list is also slow. It also gives you O of n time. Binary search tree is giving you a hope. Okay. If you're able to have a complete tree or a shape that kind of looks like a complete tree, it may give you a faster runtime, like O of log of n. But that's not always guaranteed, and it's not possible. All right, let's look at the implementation. How do we implement the binary search tree? Like the code that you're looking for, this is coming from this textbook. Okay, if you want, you can use this code. If you want, you can also look at the code that is posted on the GitHub. So for the sake of understanding, okay, I'm going to show you only this code for now. And later on, if you're interested, you can go ahead and look at that code. I usually cover that code in the regular semester because students are required to work on a project and they have to copy paste code from there. But now in the summer edition of the course, like I mentioned, okay, there's no project. So yeah, it's not a requirement. So just to understand, let's have a look at this code. So we're going to define the node class. Okay, my node class is now storing a key and a value. Okay, a key and a value. Previously, when we were looking at our code, we were storing only one integer value. Okay, but now here we're using a key and a value pair. And then, of course, this particular implementation is defining left and right. There's no parent definition. Okay. Now, this implementation is a bit optimized. It's interesting, and it's using recursion. So when you write code using recursion, Okay, using much optimized code, the size of the code will become very small. But on the other hand, you have to pay a lot of attention to understand this. Okay, so public node key and a value, that's a constructor, and we're simply assigning the values over here. Let's have a look at the BST class. In the BST class, we're going to define the anchor or the root of the tree. So we're going to define it as node root, and then we're going to define within this class, either you can have the embedded node class, or you can have it in a separate file like what we did before. And then we're defining some other methods like put. Put is just like insert. Get is just like search. Delete, of course, is delete. Okay, and then there's an iterable. So for now, let's forget about this thing. We're going to talk about it later because it's not really that necessary. Okay, so let's look at the get method. Get is just like search. You want to search something. So here the logic is your tree is storing 2 values per node. The first value is a key and the other one is a value. So what happens over here is we're assuming the user is going to provide the key. Your job is to go and search for this key in the tree. If you find the tree, you're going to return the corresponding value. Okay? If you find the tree, you're going to return the corresponding value. If you do not find the key, you're going to return null. So let's see how this works. So public value, that's the return value. Get is just like search, and we're passing it the key. We define node x equals root. So x works just like temp. While x is not equal to null, okay, we're using a compare to method. So we're defining integer compare equals key dot compare to x dot key. So what this method does is it simply compares the value, the key stored in the node with the key provided to this method, which is a parameter of this method. So the value is either going to be 0 if they're equal, -1 if it is less, +1 if it is larger. Okay? So remember this thing. If the return value of compare to is negative, this means we have to go left. If the return value is larger than 0, this means we have to go right. If the return value is exactly 0, this means we've found it and we're going to return the value. Okay? So if the loop finishes, this means that we've reached the end of one of the branches. We've reached the end of one of the branches. We're going to return null. Returning null means what? Anybody?
Search miss, Doctor.
Okay, good. Miss means that we were not able to find anything. Good. Okay. So just to understand, okay, I'm going to keep this here and just give you a demo of this. Let's play it on this tree. Okay. So we start from here. Let's say I'm searching for 8. I'm searching for 8. Okay, so here key is 8. So we're going to go like this. Node x equals root, so x, this becomes x. While x is not equal to null, it's not null. So we're going to compare this now. We're going to compare key, this one, dot compared to x dot key, the one inside this node. So we're comparing 8 with 7. 8 is larger than 7. It's going to give you a positive value. So we go and check if CMP is positive. That's not true. This would be true. So we're going to say x equals x dot right. So we go over here. X comes over here. Okay, x comes over here. Again, loop. X is not null. So we're going to compare 8 with 10. That 8 is smaller than 10. So it's going to give you a negative value. We go and compare this one. This is less than the compared value, so we have to go left. So we go left. We're going to go to 8. Okay, next we go back again. Again, x is not null. So now we compare 8 equals 8. Yes, it's going to give us 0. So this is not true, this is not true, and this would be true. So whenever this is true, it's going to return x dot value. It's going to return 8, or whatever the value associated with it. If you're looking for something which is not there, okay, it will go all the way until the end. Let's say it was over here, it went over here, it didn't find it. So if it becomes null, it's going to return null. The loop will break and it returns null.
With this, doctor, even with the search with binary trees,
Yeah.
it takes a much shorter time than in the lists.
Again, it depends on the shape of the tree. So if your tree is skewed, that kind of looks like a linked list, it's still going to give you O of n time.
Yes.
Yeah, but generally speaking, we never get that, okay? We usually never get that. We try to make sure that we never get the worst case scenario for the BST, which is a skewed tree. But theoretically speaking, it is possible. It can happen. Okay, now let's see how we're going to insert something. How we insert something in the tree. Let's have a look at this code. Okay, so that's the entire code in front of you. It's going to look a bit complicated, okay? But if you read through it, if you try to understand it, that's going to make sense. Okay, let's start looking at it. So public void put. Put is just like insert. We're passing it two variables, key and value. And we say root equals put, root, comma, key, comma, value. So you can see this thing. This is an overloaded function. So the first function has two parameters. The second function is a private method. It has 3 parameters. All right, let's look at the private method. So it's taking node x, comma key, comma value. Okay, you'll notice this. We're doing it this way because we want to have a recursive function. Recursion is a bit difficult to understand. You'll see this thing now. So we're checking if x equal null. We're going to return a new node. We're returning a new node, key, comma, value. Okay? Integer compare equals key dot compare to x dot k. So this is similar to what we did before. We're comparing the value. If it is less than 0, okay, we're saying x dot left equals put x dot left key value. Else go right. X dot right equals put x dot right key value. If it is equal, we're simply going to say x dot value equals value. So just overwrite the value and return x. Notice there's no loop here. So how is the looping going to work? Did you see recursion somewhere?
No, doctor.
No recursion? Come on.
I think put this is the recursion.
This is the recursion. It's
Yes.
calling itself. This method is calling itself. Okay. Let me explain how this is working. Okay, let's look at this little example over here. So imagine I would like to insert something. Let's say let's say, just for the sake of understanding, I can store 6.5. Okay, I can store, let's say 6.5. Let's say 6.5 goes here, right? Do you agree?
No.
Yes. 6.5.
Oh.
Start from
6.5. Okay.
6.5 is
Yes,
less
yes.
than 7. Go left, bigger right, and then we insert this over here. But how is this going to work? Let's look at this code now. So we're going to start from the beginning. Okay, of course, x is going to be here. Okay, now what happens is we're going to call this. If x equal null, is it null? Of course not. So we're going to compare x with this value, 7. So 6.5 is less than 7, which means it should be this one. So we do a recursive call. We're going to say x dot left, okay, x dot left is equal to recursive call x.left. So basically, x comes over here. Okay, this is what just happened. So we're going to call this method again. Okay, now x is on 4. This is recursive call. So again, compare 6.5 with 4. This time 6.5 is bigger than 4, which means we compare. It's not true. This is true. So we go right. Now we're going to say x.right equals put x.right. So we go right. So now this becomes x. Again, recursive call. Okay, again, we're going to check. Of course, x is not null. We compare. 6.5 is bigger than 6, so we need to go right. So this is not true. We go here. So again, what's going to happen is we're saying x.right equals to put x.right. So we're recursively calling this method. Okay, x goes over here. But notice this does not exist yet. It's not there yet. So what will happen to x? What's the value of x now? Come on. What's the value of x? Right now, see, 6.right is empty. So if I said x.right, recursive call, x would be null.
Yes, it will.
Okay, x would be null. So when I come over here, it's going to say if x equal null, yes, it is null. So it says return new node. Means that you create a new node, and of course you're going to put all these values inside. So you're going to put 6.5 over here. Okay, it says return this node. Now, what's really clever, how this method is written very cleverly, is when they return back, okay, the method which called it was this one. So here we're saying x dot, so x becomes this one. We're saying x.right equals to this new node. So this is what's going to happen. It's going to connect the new node, okay, to this node, x.right. Now this connects to this one. So now it's going to recursively go back all the way until the beginning, and we have actually attached this in there. Does it make sense to you?
Yes, definitely.
Okay, I understand this is difficult to understand, even in regular semester. Okay, this code is very well written, very optimized. So looking at it again and again will make you understand what's actually going on. But don't worry about it. Okay, we're going to look at the other code. I'll show you the other code after this. So I have only 1 or 2 more slides, and then I'm going to stop, and then we're going to have a look at the code. Okay, so summing up, so far what we've studied, the best case for a binary search tree is if you have a tree which is almost a complete tree. Typically, we don't get something like this. We get something which is skewed on one side. Worst case scenario is if your data is pre-sorted and you try to insert it, that's going to give you a shape which looks very similar to a linked list. Whose runtime is, of course, O of n. So here's a little bit of a simulation. Okay, let's look at the simulation. We're trying to insert 255 values in an empty tree. Let's see what happens. See the shape of the tree. Is it a complete tree?
No, it's not
Yes.
complete.
Yeah, it's not complete, it's not skewed. It's something between, which is a typical case. Okay? So most of the time, the tree's runtime is going to be close to log of n. Okay, so here's a summary. If you look at the binary search tree, okay, the average case for search and insert is 1.39 log of n. How did we get this? Based on experimental evaluation. Okay, remember we talked about experimental evaluation 2 weeks ago. So 1.39 log of n, that's the runtime for an average case. But if somebody says, no, give me a guarantee. Okay, so the guarantee is the worst case scenario, that's a big O, and which is big O of n, because there is a possibility your tree can look like a completely skewed tree, which is going to give you O of n.